Hey guys, today we are going to talk about quantum computing. Firstly, what is quantum computing and how it was discovered? Quantum computing is the use of quantum mechanical phenomena such as superposition and entanglement to perform computation. Computers that perform quantum computation are known as quantum computers. Quantum computers are believed to be able to solve certain computational problems, such as integer factorization, which underlies RSA encryption, significantly faster than classical computers. The study of quantum computing is a subfield of quantum information science. Quantum computing began in the early 1980s, when physicist Paul Benioff proposed a quantum mechanical model of the Turing machine. Richard Feynman and Yuri Manin later suggested that a quantum computer had the potential to simulate things that a classical computer could not. In 1994, Peter Shor developed a quantum algorithm for factoring integers that had the potential to decrypt RSA-encrypted communications. Despite ongoing experimental progress since the late 1990s, most researchers believe that fault-tolerant quantum computing still a rather distant dream. In recent years, investment into quantum computing research has increased in both the public and private sector. On October 23, 2019, Google AI, in partnership with the U.S. National Aeronautics and Space Administration, NASA, published a paper in which they claim to have achieved quantum supremacy. While some have disputed this claim, it is still a significant milestone in the history of quantum computing. Quantum computing is modeled by quantum circuits. Quantum circuits are based on the quantum bit, or qubit, which is somewhat analogous to the bit in classical computation. Qubits can be in a 1 or 0 quantum state, or they can be in a superposition of the 1 and 0 states. However, when qubits are measured, the result is always either a 0 or a 1. The probabilities of these two outcomes depend on the quantum state that they were in immediately prior to the measurement. Computation is performed by manipulating qubits with quantum logic gates, which are somewhat analogous to classical logic gates. There are currently two main approaches to physically implementing a quantum computer: analog and digital. Analog approaches are further divided into quantum simulation, quantum annealing, and adiabatic quantum computation. Digital quantum computers use quantum logic gates to do computation. Both approaches use quantum bits or qubits. Any computational problem that can be solved by a classical computer can also, in principle, be solved by a quantum computer. Conversely, quantum computers obey the Church-Turing thesis, that is, any computational problem that can be solved by a quantum computer can also be solved by a classical computer. While this means that quantum computers provide no additional power over classical computers in terms of computability, they do in theory provide additional power when it comes to the time complexity of solving certain problems. Notably, quantum computers are believed to be able to quickly solve certain problems that no classical computer could solve in any feasible amount of time, a feat known as quantum supremacy. The study of the computational complexity of problems with respect to quantum computers is known as quantum complexity theory. Next is about quantum computing models. There are a number of quantum computing models, distinguished by the basic elements in which the computation is decomposed. The four main models of practical importance are: first, quantum gate array, computation decomposed into a sequence of few qubit quantum gates. Second, one-way quantum computer, computation decomposed into a sequence of 1 qubit measurements applied to a highly entangled initial state or cluster state. Third, adiabatic quantum computer, based on quantum annealing, computation decomposed into a slow continuous transformation of an initial Hamiltonian into a final Hamiltonian, whose ground states contain the solution. 44. Fourth, topological quantum computer. 45. Computation decomposed into the braiding of anyons in a 2D lattice. Fifth, the quantum Turing machine is theoretically important, but the physical implementation of this model is not feasible. All four models of computation have been shown to be equivalent, each can simulate the other with no more than polynomial overhead.